Before showing my project, I want to quickly use these slides to talk about my experience of using Rust compared to using C++ on this project. One thing I noticed in this project is that all variables in Rust are immutable. You must explicitly state if you want the variables to be immutable at all. I found that having all variables immutable made it easier to debug, as you know what parts are moving, what parts are not. Unlike C++, Rust compiler can figure out variable types without explicitly mentioning them, but you must initialize those variables. However, while this works most of the time, I've noticed that sometimes the compiler makes mistakes, especially when using structs, user-defined structs for the first time, where you then you have to explicitly mention the typing for those. Otherwise, it works well. Another thing I noticed that Rust and C++ does have object-oriented programming. I know Rust doesn't really have it. It uses structs, but it mimics it really well. Another thing I noticed that Rust has no runtime, but is able to figure out most of its errors before even running the program. Another thing I noticed are both programs both have like pointers. C++ and Rust both have raw pointers, but Rust is more safer as it has box pointers, which are safer, allowing you to like reference much easier. Another thing which was a huge problem during this project is Rust does not have comparators. So when you're using priority queue, you cannot decide what comparator you use, like in C++. All the ordering is defined by the struct itself. So if you define a struct, you also define the ordering, and that is set in stone. You must use a wrapper to deal with it. Like in my project, I had to deal with this, and you will see that later. Also, two changes. I did a little bit of changes from the homework version. I got rid of header files. I don't think I don't think Rust supports header files, and I implemented most of the files in the C++ homework. Before running this project, let me explain how the project works. I'll first start by explaining the miscellaneous stuff such as the structs I use in this project, as well as the input files. In this project, I have three user-defined structs, which are process, durwrap, and pair. The process struct contains essential information about each job, such as the arrival time, duration, the time it first ran, and its completion time. I have kept the struct unchanged from the homework as it was the most intuitive way to store the information. In Rust, there are no comparators, so each struct must come with their own predefined comparison mechanism, which is useful for priority queues. In the case of process, we sort by the smallest arrival time. And here's the code for the creating our own ordering for the process. Durwrap is a wrapper for the process struct. The durwrap struct contains only one field, which is the process. I needed a durwrap because Rust does not let me have comparators, so each struct must come each struct comes with their own predefined ordering system. And since there is no direct way to change the ordering system of process, which is based on the smallest arrival time, I need to wrap it around durwrap, which introduces a new ordering system that allows me to order by the smallest duration. The pair struct is another wrapper. Pair stores a process in the remaining time till the job is completed. Similar in this, it follows a similar reason why I use durwrap. I created pair struct to enable me to sort by the remaining time, and as well as keep track of time until job completion. The project first reads in the data file. The data file is exactly the same as the data file received in homework 3, where the first number is the arrival time and the second number is the duration of the job. Read and load simply just reads in the data and creates a binary heap or a priority queue of processes or the jobs, which are sorted by the arrival time, and stores into a variable called workload. Workload is passed into each of the algorithms, such as FIFO, Red Robin, etc. But to pass it as a value, we first need to clone it and pass that in. Here is the FIFO algorithm. The FIFO algorithm operates based on the arrival time of the job and does not take into consideration their duration. Within the algorithm, we iterate through all the jobs in the binary heap and update their values. For each job, it starts by updating the job's first run field and increments the current time variable by the duration of the job, simulating the job being worked on. Sequentially, it updates the job's completion field afterwards. When the job is completed, we add it to the completed list and return the list. This is the shortest job first algorithm. The shortest job first algorithm operates by prioritizing jobs based on the shortest duration, focusing only on those that have arrived rather than those that will arrive in the future. The algorithm consists of 3 while loops. The outer while loop ensures that all jobs are processed, while the inner loops ensures that we work on jobs with the shortest duration among those that have arrived and perform operations on those. Inside the first while loop, we immediately enter the second while loop. The second loop, as mentioned earlier, retrieves all arrived jobs and sorts them based on their duration. To sort by duration, we have to use the dir wrap on the process struct. Moving on to the third loop, we essentially carry out the same operation as the 5-while algorithm. We iterate through each of the jobs, updating the first run field, incrementing the time, and populating the job completion field. And we repeat these steps until all the jobs are completed. STFC algorithm is similar to the SJF algorithm, but considers future jobs that may come. Similarly, the algorithm has 3 loops that perform similar tasks. However, there are 2 main differences. The first difference is the use of pair wrap struct instead of the dir wrap. It is used to keep track of how much time is remaining until the job is completed, and it is also used to sort by the shortest remaining time on the priority queue. The second main difference lies in the implementation of the third loop. In this section, we operate on jobs with the shortest time until completion among those that have arrived. If a job hasn't been run before, we simply update its first run field. Next, we need to check if there's a future job by examining the workload priority queue. If there are any, we need to keep track how much time until the next job appears by using the variable next job in, which is obtained by calculating the difference between the arrival time of the future job and the current time. Until the new job arrives, there is no upcoming jobs. The code behaves similar to STFC. However, if a new job arrives or next job in equals 0, we need to stop working on the current job and push it back into the secondary priority queue with the new remaining time. We then break out of the third loop and add the new job into the current job list. From there, we select the new job with the smallest remaining time and repeat the process until all the jobs are completed. The round-robin algorithm operates on each job for a short amount of time before switching to another job and repeating the process until all jobs are completed. The implementation of round-robin is quite similar to the implementation of STFC with a few changes. The first difference is with work list, or the list of jobs that have arrived. In RR, the work list is organized as a queue without any sorting metrics in order to provide each process with a fair opportunity of CPU time. The third loop, instead of attempting to complete the job in one go, we only allocate 1 second of processing time to each of the job before moving to the next one. And we repeat this process until all jobs are completed. Finally, these are the metric functions. Print metric iterates to the list of completed jobs and prints out the fields of each of the processes, and as well as calculates the average turnaround rate and calculates the average response rate using the corresponding functions from here. To use the algorithm, simply enter a valid data file and run it. Then you should get the metrics for all the scheduling algorithms, like right now. Here are the results, and we could change the file to get different results too.